Welcome to AP Chemistry at Heineniga High School, and today we'll be looking at information to help us get ready for the Chapter 17 test. Some of the big areas, units like always, and then the big three is really buffer situations, titration situations, and KSP issues, because those are the three major areas we did calculations in this chapter, and they all have things to be careful of. One, don't forget K in all of its forms, whether it's a KA, KB, KSP, no units. Don't forget when it's a weak base, you need a KB, not the Ka that's probably given. And remember, Ka times Kb equals Kw, which you can use to solve and go from one to the other. Also, don't forget in a Ka problem, X is going to equal H3O plus, but in a Kb problem, X is going to equal OH minus. And don't forget, because this is really handy in titrations, pretty much whenever you see you have the molarity and the volume, you're going to be changing the volume into liters and multiplying to find out how many moles you have. We do that over and over and over. And usually if you see both of those things in the problem, sooner or later you're going to be calculating the number of moles. Don't forget whenever you mix solutions, and this is particularly an issue when we get into KSP, you have to change the concentrations. Mixing aqueous solutions is going to change the concentration. Don't forget you need to use M1V1 equals M2V2, where the V2 is the total volume. Number 6, don't forget a quick sig fig issue. P-values, the number of decimal places, is used to represent the number of sig figs. And don't forget, there's a difference between solubility and molar solubility. Most of the time we deal with molar solubility, but converting between the two is really just a molar mass conversion. Now, what makes a buffer? Buffers are one of the major types of math in the chapter that you need to have a working understanding of. And you need to understand, fundamentally, there's three different ways to make a buffer system. When you have a buffer system, you have a weak and its conjugate base in significant quantity. And you can't get it by just throwing the weak acid in water, because it's only going to dissociate partially, which means you get a bunch of HA, but you don't get very much A minus. So whenever you have a weak acid or a base, just by throwing it in water, you never make a buffer system. So how can we make a buffer system with a significant quantity of a weak and its conjugate in solution? Well, the simplest way is to have a weak acid or a base in water and then add its conjugate from a salt. So like acetic acid, that's a common weak acid. Sodium acetate has the conjugate of acetic acid, which is going to be, if you dump it in water, a water-soluble substance that contributes the acetate anion. So we would have our weak acid, acetic acid, and the acetate anion in significant quantity. And we can do the same thing with bases. Ammonia is a common weak base. Ammonium chloride would have its conjugate. So if we have both of those in solution, we would form a buffer. So that's the easiest way, is to just have the weak and its conjugate by getting its conjugate by throwing in a salt and dissolving it that contains the conjugate. Now, the second and third ways are the ones that students often struggle with on the AP test, which means they often struggle with it on my test as well. And that is the concept of partial neutralization. If we have a weak acid system and we partially neutralize the weak acid, we make its conjugate base. Now you can see here in this reaction, and by the way, this should be a single arrow there because we're not talking about an equilibrium reaction in this case. When we neutralize our acetic acid by adding a strong base like OH minus, the acetic acid is becoming its conjugate in the process. And the key word here is partial neutralization. If I partially neutralize this, I still have a significant quantity of it, and I'm going to make a significant quantity through neutralization of its conjugate, therefore making a buffer system. And I can do the same thing. If I have a salt that contains the anion, and I throw it in water, I'm going to have a significant quantity of the acetate anion, which is an active conjugate base. But I don't have a buffer system because as a weak base, it doesn't ionize into acetic acid all that much. But if I put acetic acid in water, yes, I'd get a buffer system. But the way to get it that you need to understand that students often forget is the partial neutralization idea. Well, this is a weak base. So it's neutralized by a strong acid. So if I add a strong acid, then that's going to contribute H+, that's going to make its conjugate. And once again, it has to be partial neutralization. If I partially neutralize the acetate anion with a strong base, or with a strong acid, I'll end up creating its conjugate, acetic acid. So don't forget, we can partially neutralize the weak, or we can partially neutralize its conjugate by adding the other type of strong. So don't forget the partial neutralization to make buffer systems. Now, the next area is titrations. If you don't have a buffer, look closely and see if you're titrating an acid with a base. And the most important thing to do once you realize, okay, this is a titration problem, is you need to understand, is it weak, strong, or strong, strong? Because they're different. So the very first thing, you have to know your strong acids and bases. If you don't, then it's going to be a 50-50 guess whether it's strong, strong, or weak, strong. So make sure you know your strongs. If it's not one of your strongs, it's a weak. Now, in both cases, whether it's strong, strong, or weak, strong, the very first thing we need to do is determine how much H plus and OH minus we have available for neutralization. Because that's what we're doing in a titration, is we're taking a weak or strong acid and we're slowly neutralizing it towards its equivalence point and beyond with its opposite strong. So if it's a weak strong, the math is a little bit more complicated, so we're going to look at that one first. But where you're at in the titration is still going to depend upon finding the moles of H plus and OH minus from your acid and your base and comparing the two. And in each step of the way, that can often be a very, very, very important thing. Now, before the titration begins, that's our first region in a titration, all we have is our weakened water that's partially dissociated into its conjugate. So you have a little bit of the conjugate, a whole bunch of the weak, and then you also have water present. Well, this is a chapter 16 question. This is just a Ka or a Kb, depending on which it is that we've thrown in water. So if you remember, if it is our typical weak acid, we call that HA. The equilibrium system we establish when we throw that weak acid in water is the one that's listed here. But remember, even though we talked about this idea a second ago, we don't have a significant quantity of both of these. So before the titration begins, we just have a typical x squared over the concentration minus x equals the Ka, and we neglect x to end up with a very simple H plus is going to equal the Ka times the HA square rooted. So before the titration begins, it's just a chapter 16 calculation, just like we looked at in chapter 16. Now, once we start the titration, then we start to neutralize our weak acid a little bit. But what you need to understand is it's still the same equilibrium system. So we're still talking about this reaction, and the Ka expression for that reaction is really our driving equation. So it's going to be H3O plus times the concentration of A minus all over the concentration of HA. So the math is the same, really, math as in region 1, but in region 1, the H3O plus and the A minus were equal to each other, and that's where x squared came from. Well, in this case, when we have a buffer, we have a significant quantity, we've shifted the equilibrium system, and we no longer have the same amount of H3O plus and A minus. So it's the same equilibrium system driven by the same equilibrium expression, but because of neutralization with a strong base, and you can see here, HA is making A minus. So the key to this type of problem is to find out how much of this we have and find out how much of that we have through neutralization. So you're going to take your moles of H plus and subtract from it the moles of OH minus from your weak and strong, and the H plus is going to be larger. How much do we have left? That's going to give us our H plus mole amount. And if we divide that by our total volume in liters, then we would have our concentration for our buffer problem. And the same thing would be true with the A minus, except you need to understand that A minus is coming from the reaction of HA and OH minus, and OH minus is completely used up. And it's a one-to-one stoichiometry between the OH minus and the A minus. So if we know our moles of OH minus, then we know our moles of A minus, because it's going to be the exact same. And once again, take that and divide by the total volume. And remember, that's important. It's got to be the total volume in liters. Then we would have the two concentrations we need in this calculation up here to solve. Now, one of the things that I strongly recommend with buffers, and this is true of any buffer problem, so what we talked about in the last slide was making buffers, but here is our buffer equation. It's just a form of that equation up there, and it's worth remembering because it makes the process a whole lot easier. Technically, a buffer problem is a double neglect X problem, and it's an icebox setup, But fundamentally, it's going to come down to this every single time. The H plus is going to equal the Ka times the ratio of the concentration of the acid, that's our HA as a general formula, over the concentration of our base. And this works every single time we have a buffer. So if we find this and we find that, we plug them in this equation and we calculate the H plus. Now, one thing that's worth noting here is these two substances, HA and A minus, are in the same beaker, which means they have the same volume that you would plug in here. So we really don't have to do this step. Once we know moles of H plus, we can put that up there. Once we know moles of A minus, we can put that down there, because the ratio of those two mole amounts is going to equal the ratio of their concentrations. And that's a quicker, easier way to do it. So just leave it in moles. Now, the other thing of importance at this part of the titration is what's called the half equivalence point. And if we're talking about the region before the equivalence point, the most important region is our half equivalence point, because at the half equivalence point, the concentration of the acid and the base are equal, because we've half neutralized our acid, creating an equal amount of base. And therefore, it's Ka times 1, so H plus equals Ka, and therefore pH equals pKa. If you know what weak acid you've got, it's very, very easy to find your pH at the half equivalence point. And if you know what the equivalence point volume is, that's going to be half of that as a volume. So you'd put a dot at that point. It's a quick, easy point to find in that region before the equivalence point, which brings us to that step. Once we've 100% neutralized, what we're going to have now is a weak base in water. Because all of our HA has been neutralized, technically there's none of it left. We've converted HA into A minus, so now we have a bunch of A minus. Now, that's in a water solution, so that's going to undergo hydrolysis with the water by this reaction. Well, this is our Kb reaction, and like above in region 1, it's our neglect x squared situation that we saw last chapter. It's just for Kb. So OH minus would equal to Kb times the concentration of our base A minus square rooted. So that's the key to this section. Now, we need the concentration of A minus, and that's critical. So when we get A minus, we have to remember we're going to know the moles of A minus, and that's actually going to equal the moles of H plus if we're at the equivalence point. So whatever that was in earlier calculations, if you did any before the equivalence point, we know exactly what the moles of A minus is going to be. They're the same thing, which at this point would also equal the moles of OH minus from our strong base. So once we know our A minus, we just divide it by the total volume in liters in order to get this concentration. We can't leave it in moles like we just talked about doing for our buffer region, because we don't have a ratio of two things in the same beaker that we're looking at. We're just looking at the concentration of A minus here. And then after that, region 4 is actually the one region that's similar between both processes, and that's after the equivalence point. What we have left at this point is, yes, there's still A minus. We still have our weak acid, but that becomes irrelevant when we leave extra OH minus from our strong base neutralization. And that OH minus in its concentration is going to drive the H3O plus and therefore the pH of our solution, our water solution. So after the equivalence point, we just take and subtract not our moles of H plus minus moles of OH minus, but the opposite. So we can find out how many moles of OH minus are left. If we divide by, once again, the total volume in liters, we would now have OH minus from which we can calculate the pH. So that is our weak strong titration. Now, strong goes a lot quicker, because in a strong titration, the math is significantly easier. And it's pretty much the same kind of math that we do the whole process, or we get to skip the math. Now, first is before the titration begins. What we have is a strong acid in the flask. And if we know the concentration of our strong monoprotic acid, the concentration of the H plus is going to equal the concentration of the monoprotic acid. Therefore, we can quickly get pH from that. And if it was a strong base, we can find from the OH minus the POH, subtract from 14 to get our pH. So before the titration begins, it's just a strong acid or base problem right out of chapter 16. Now, once we start the titration, and we're before the equivalence point, what we have is extra acid. And once again, our extra H plus is going to drive our pH. So find moles of H plus from our strong acid and moles of OH minus from our strong base, subtract and divide by the total volume, and you've got your H plus concentration. Take the negative log of that, and you have your pH. Now, once we get to our equivalence point, the math is easy because the neutralization that occurs is going to cancel our H plus and OH minus. And unlike in a weak where we had a conjugate base or acid left over to change the pH, what we have here are two inactive cations and anions left over from our strongs that aren't going to affect the pH. So 100% of the time in a strong, if you're at the equivalence point, your pH is going to be 7 because your H plus is going to equal your OH minus, which will equal 1 times 10 to the negative 7th when we're at room temperature. And honestly, we're pretty much always at room temperature, so this is always going to be true. And then finally, the last region is our after the equivalence point. And remember, this is the one that's the same as the weak strong. You'll notice the calculation is identical. We calculate the moles of OH minus from our strong base, subtract from that the moles of H plus from our strong acid, divide by the total volume, and we've got our OH minus concentration from which we can generate the pH. So that's a strong titration. Now, the next thing I want to briefly look at here is the common ion effect, because it's something you should have a working knowledge of mathematically as well as conceptually for the test. Now, remember what we're doing here is we have some weak equilibrium system, a weak acid in water, a weak base in water, and to that we've added a common ion, and it's an ion common to the two things on our product side. In this case, if we added a source of F minus, or if we added a source of H plus, then we would be shifting equilibrium to the left, and that means it's going to ionize to a smaller degree. So that's fundamentally all there is to the common ion effect, is it's an equilibrium shift by Le Chatelier's principle. If we add either product ion, that's going to shift equilibrium to the left, decreasing the percent ionization of our weak. Now, mathematically, what that looks like is really a double neglect X situation. So fundamentally what we're doing here, and remember buffer is an application of this. So here's a typical problem. We've got an equilibrium system, HF in water, that's our weak. And you'll notice in the problem, it's asking us to find the pH. It gives us the concentration of our weak acid. And it also gives us the concentration of a strong acid, because that strong acid is going to contribute this. So this is a common ion effect problem. Now, in this particular case, as equilibrium shifts here, that's going to end up affecting the pH of the system. And as a equilibrium problem, we've got our equilibrium expression that's right here. And that's going to equal our Ka, in this case, the Ka of HF. Now, because H plus is contributed by the strong acid HCl, we know that in our typical problem from last chapter where both of our products would be 0 and then from there we approach equilibrium, one of them is going to be a non-zero. It's still going to shift to the right and we still use the stoichiometry, but now we're looking at an icebox and we end up with two terms that involve a number plus or minus an x. And just like last chapter, if that x is small enough, we can neglect that x. The difference is in this case, we can neglect both of those x's. So what we end up with is the bottom expression that we see. If we don't neglect the x's, we're going to be stuck with a quadratic. So by doing the double neglect x here, we simplify dramatically our calculation of x. And in this particular case, x is going to equal the F minus concentration. If that's what they ask us to find, at this point we would be done. And if they're asking us to find the H plus, well, we added a bunch of our strong acid. It's going to be 0.10 molar H plus. And from that, we can calculate the pH. Now, the last thing we're going to look at is KSP type problems. Now, one common application of a KSP equilibrium system is being asked the question, will it precipitate? If you ever see the question in this chapter, will it precipitate? This is a KSP problem. It's going to be a low solubility ionic substance that reaches an equilibrium system quickly when it gets thrown in water because you quickly reach the point where it's saturated. So your rate of dissolving equals your rate of crystallization. We have equal and opposite rates in a closed system. We have equilibrium. Now, one of the nice things about the equilibrium expression when we have a KSP is what's on the reactant side is always a solid, so that's going to simplify our KSP expression significantly because it's always going to be, in essence, be over 1. Now, if we have a precipitate type question, what we're actually doing is we're going to be given or able to find out these two ion concentrations, we can plug them in and we can calculate. Now, since we don't know if we're at equilibrium and we reach saturation, when we plug these two ion concentrations in, we're going to get a Q rather than a K. And what we do is we compare Q to K. Now, if Q is equal to K, then we're exactly at equilibrium and we have exactly a saturated solution. That's a pretty rare thing on a particle level to have exactly the same to within sig figs. So most of the time, Q is going to be too small, which fundamentally means the ion concentrations were too low to reach equilibrium, and therefore we do not have a precipitate. Or the Q value is going to be greater than the K value, which means the ion concentrations were large enough to reach saturation, and the extra ions are going to precipitate out as our salt. So basically what happens is when we got a Q greater than K is those ions keep recombining until we get to saturation. And technically, now we have a situation where Q equals K again. And we're going to have a bunch of solid left in there, so we had to precipitate. So remember, when you're doing this kind of calculation, find the concentration of the ions, plug them into the KSP expression, and compare that to the known KSP. And be careful. Most of the time when you're doing this, you're combining solutions, which means you're changing the concentration. So this is an application where you usually have to do M1V1 equals M2V2, and V2 will be the total volume of the two aqueous solutions in order to calculate your new concentrations after mixing. Now, don't forget then, look at the question in almost every case when you're doing a mixing volume problem, or a mixing ions in a low solubility salt and ask if there's a precipitation, you're going to have to use M1V1 equals M2V2 to fix the volume and therefore fix the concentration. Now, the last thing I wanted to hit was some common confusion that happens with KSP. It's a pretty simple equation. And if we're given the concentrations, we can plug them in and we can calculate to get our K, as long as they're saturated concentrations of our relevant ions, in this case Ba2 plus and F minus. If we know those two concentrations, we could plug them in and we could calculate K. Now, one of the common mistakes students make, because we talk about this relationship between the molar solubility, our S relationship that we look at, and the KSP, and the concentration of the ions at equilibrium or at saturation, all those things can be related to each other in this equilibrium system by the stoichiometry. But that's only going to be true if we make this system by dissolving this solid in water and we don't shift the equilibrium in any way through Le Chatelier stresses. Then it would be true that for every 1 barium fluoride, I get 1 barium and 2 fluorides. And students remember us talking about if Ba is X, then F minus has to be 2X. So they start to get too happy and they do this. Remember, this is not valid. While it is true if you make this equilibrium system by throwing a solid in water that the fluoride will be twice the barium, you don't put 2 times the fluoride in there. You calculate what the fluoride is, twice the barium, and that's what you plug in there, and you just square that term. And that's a common misconception once we get into the S squared 4S cubed solubility relationship to KSP type problems. And people start to inappropriately plug that 2 in a variety of places. So just fundamentally realize that in this particular case, if I establish this equilibrium system by throwing barium fluoride in water, it would be true that if I had S bariums, and that would represent the molar solubility of the barium fluoride, one of those breaking apart to 1, so S of them dissolving to S, then I would get S of those. Now fluoride is going to be twice barium, so that's my 2S. And when I plug that 2S into my equilibrium expression here, you're going to square it, and you end up with S times 4S squared, which gives us 4S cubed. Remember, this relationship, that equals KSP, is only true if we haven't shifted the equilibrium system. And remember, S represents our molar solubility, and we can also use it to find our concentrations of barium and fluoride at equilibrium, at saturation. This is completely inappropriate and false if we have shifted this equilibrium system, because if I've added barium, that's going to shift equilibrium to the less, that's going to drop my fluoride, and my fluoride is no longer going to be twice my barium. So you need to understand when you can use the S relationship to KSP and when you can't. This relationship is always true. No matter what we do, it's still going to multiply out to K. But it's not necessarily going to be true that K is going to equal the solubility cubed times 4. That's only going to be true if we form the system by dissolving the barium fluoride in water. And then the S relationship is valid. If we do anything to shift equilibrium, mixing ion concentrations, playing with pH, in this case, fluoride is an active anion, which means if I play with pH, I'm going to change my fluoride concentration. That means the S relationship is going to go out the window. Or things like common ion. If we add barium nitrate, that's going to shift. If we add sodium fluoride, that's going to shift. And in all those cases, this S relationship here is going to be invalid as soon as I do that. But it's perfectly valid and almost always what you're going to be using when you form this system by just dissolving the low solubility substance in water. And that ends our note recap for this test.